The gunner tracked the bomber through his predictor sight as it crossed at 12,000 feet, calculating lead time, altitude, and speed in his head while his crew frantically adjusted the fuse settings on the 5-inch shells. 22 seconds of flight time. Set the mechanical time fuse to 22 seconds. Load. Fire. The gun bucked. The shell climbed. 22 seconds later, a black puff of smoke appeared in the sky, roughly 300 feet behind and 200 feet below where the bomber had been when they fired. Miss. Load another shell. Reset the fuse. The bomber was already a half-mile further along its flight path. Calculate again. Fire again. Another miss. This was anti-aircraft warfare in 1942, and it was failing catastrophically. American gunners aboard ships in the Pacific and at coastal installations were discovering what their British counterparts had learned over the skies of London 2 years earlier. Hitting a fast-moving aircraft with an explosive shell was mathematically, practically, and consistently impossible, using the technology they had. The shells exploded on timers, crude mechanical fuses set by hand before loading. If you guessed wrong about the bomber's altitude, speed, or course by even a small margin, your shell exploded harmlessly in empty air. The bombers flew on, the ships burned. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But in a laboratory at Johns Hopkins University in Baltimore, Maryland, a physicist named Merle Tuve was working on something that the Navy Bureau of Ordnance had already declared impossible. He was building a fuse that could think, a fuse that could detect when it was near an aircraft and detonate itself automatically at exactly the right moment, without any human calculation, without any mechanical timer, without any guesswork. A radio fuse, a proximity fuse. The Navy's ordnance experts had reviewed his preliminary designs and rejected them as impractical, too complex, too fragile, too expensive. The fuse would have to survive being fired from a gun at accelerations exceeding 20,000 times the force of gravity. It would have to work reliably in all weather conditions. It would have to be manufactured by the millions. Impossible. Tuve ignored them. He assembled a team of physicists, engineers, and technicians and told them they were going to build it anyway. They were going to break every rule about how vacuum tubes could be made, how radio transmitters could be miniaturized, how circuits could be designed. They were going to solve problems that experts said couldn't be solved. And they were going to do it in months, not years, because American sailors were dying in the Pacific, while Japanese bombers attacked with near impunity. What Tuve and his team created would change naval warfare more profoundly than almost any other invention of World War II. It would increase the kill probability of anti-aircraft fire by a factor of 5 compared to conventional fuses. It would be so valuable, so revolutionary, that it would be classified at a higher security level than the Manhattan Project in some contexts. The British would call it the most significant development in warfare since radar, and it would all begin with one engineer's decision to ignore what the experts said was possible and build something that by all conventional wisdom should not work. To understand why the proximity fuse seemed impossible, you need to understand the fundamental problem of anti-aircraft warfare as it existed in the early 1940s. Aircraft were fast, typically flying between 200 and 300 miles per hour. They could change altitude and direction. They were small targets at combat distances, often appearing as dots against the sky, and the shells fired to destroy them were ballistic projectiles that followed predictable arcs through space, traveling for 20 to 30 seconds before reaching altitude. The math was brutal. A 5-inch naval gun firing at an aircraft at 10,000 feet would send its shell on a trajectory lasting approximately 25 seconds. During those 25 seconds, an aircraft traveling at 250 miles per hour would cover nearly 2 miles. The gunner had to predict not where the aircraft was, but where it would be 25 seconds in the future. If the aircraft changed course even slightly, or if the gunner's estimate of altitude was off by just 500 feet, the shell would explode hundreds of feet away from its target, completely harmless. The shells used time fuses, mechanical devices set by hand before loading. A crew member would receive altitude and range data from a fire control system or predictor, calculate the time to target, and physically adjust a mechanism on the fuse to that specific time interval. The shell would be loaded and fired. The fuse would count down mechanically as the shell flew, then trigger the detonator when the preset time elapsed. The problem was that every variable in this chain had uncertainty. Aircraft altitude estimates could be wrong. Speed calculations could be inaccurate. The fire control predictor solution could be based on outdated position data. The mechanical fuse itself might be imprecise, varying by a fraction of a second from its setting. Wind affected the shell's trajectory. Temperature affected burn rates in the mechanical timer. Studies conducted by the British after the Battle of Britain revealed horrifying statistics. It took an average of 2,500 anti-aircraft shells to bring down a single German aircraft. Some estimates ran as high as 4,000 shells per kill. The American experience in the Pacific was proving no better. Japanese aircraft attacked ships with relative impunity because shipboard anti-aircraft fire was so ineffective at medium and high altitudes. At low altitudes, rapid-fire weapons like the 40mm Bofors and 20mm Oerlikon could engage targets directly, shooting streams of shells and relying on volume of fire. But above 5,000 feet, these weapons lost effectiveness, and the battle became one of prediction, calculation, and mechanical time fuses. A battle the defenders were losing badly, the United States Navy understood this was a crisis. As war with Japan became increasingly likely in 1940 and 1941, naval planners recognized that American ships would face significant air threats in the vast Pacific. Japanese naval aviation was formidable, equipped with capable aircraft and well-trained crews. If American anti-aircraft defenses could not protect the fleet, the Navy's ability to project power across the Pacific would be severely compromised. Every carrier, every battleship, every transport was vulnerable to attack from above. The 5-inch 38 caliber dual-purpose gun was America's primary medium anti-aircraft weapon, mounted on nearly every major warship. It could fire 15 rounds per minute to altitudes exceeding 35,000 feet. But hitting anything at those altitudes with mechanical time fuses was a matter of luck more than skill. The problem was not new. Anti-aircraft warfare had existed since the First World War, when aircraft first became significant military threats. For more than 2 decades, engineers and military planners had struggled with the fundamental challenge of shooting at fast-moving aerial targets. Various approaches had been tried. Barrage fire, where multiple guns fired at the same area of sky simultaneously, hoping to create a zone of exploding shells through which aircraft would have to fly. Predictor systems, mechanical computers that calculated firing solutions based on observed aircraft position and velocity. Better fuses with more precise timing mechanisms. Improved fire control directors that coordinated multiple gun batteries. All of these approaches helped, but none solved the core problem. You were still trying to make a ballistic projectile explode at a precise point in space where you hoped an aircraft would be many seconds in the future. The aircraft had agency. It could maneuver. It could climb or dive or turn. The shell could not adjust course. It could only follow its ballistic arc and explode when its timer ran out. The only way to significantly improve kill probability was to increase the lethal radius of the explosion, the distance from the burst at which fragments would damage or destroy an aircraft. A 5-inch high explosive shell produced a fragmentation pattern that was lethal to aircraft out to approximately 50 to 75 feet from the detonation point, depending on fragment velocity and density. Beyond that distance, Fragments lost energy rapidly. An aircraft 300 feet away from a burst was generally safe. This meant that to guarantee a kill, the shell had to explode within 75 feet of the target, a sphere of effectiveness with a radius of 75 feet in three-dimensional space while the target was moving at hundreds of miles per hour. Getting a mechanical time fuse to trigger a detonation within that sphere was extremely difficult. Getting it to trigger at the optimal moment, when the shell was at its closest approach to the target, was nearly impossible with existing technology. Engineers understood that what they needed was a fuse that could measure its distance to the target and detonate when that distance was minimized. A proximity fuse. The concept was not new. Various inventors had proposed proximity-triggered weapons going back decades. But actually building such a device that would work reliably presented enormous technical challenges. The fuse would need some kind of sensor that could detect the presence of an aircraft. It would need electronics to process that sensor data and trigger the detonator at the right moment. And all of this had to fit inside a fuse cavity approximately 3 inches long and 2 inches in diameter, had to survive the shock of being fired from a gun, had to work at temperatures ranging from below freezing at altitude to the heat of the firing sequence, and had to be cheap enough to manufacture by the millions. By 1940, several approaches had been investigated. Photoelectric fuses that would detect changes in light levels were considered but proved unreliable in varying weather and lighting conditions. Acoustic fuses that would detect engine noise faced similar problems with background noise and reliability. Magnetic fuses that would detect the metal mass of an aircraft had insufficient range. Every approach seemed to have fundamental problems that made it impractical for mass production and combat use. The consensus among ordnance experts was that while a proximity fuse was theoretically desirable, actually building one that met all the requirements was not feasible with current technology. They were wrong. And the man who would prove them wrong was not following their consensus. He was building something they said couldn't be built, using methods they said wouldn't work, on a timeline they said was impossible. Merle Tuve was 40 years old in 1940 when the National Defense Research Committee asked him to investigate the feasibility of a radio proximity fuse. He was a physicist who had made his reputation in nuclear physics and radio research at the Carnegie Institution in Washington. He had helped develop radio techniques for measuring the ionosphere's height. He understood radio wave propagation, vacuum tube circuits, and the physics of electromagnetic radiation. More importantly, he understood that solving impossible problems often required ignoring the people who said they were impossible. The National Defense Research Committee, established in June of 1940 under Vannevar Bush, was tasked with mobilizing American scientific talent for military research. One of its priorities was improving anti-aircraft weapons. When the committee approached Tuve about developing a proximity fuse, he immediately grasped both the military necessity and the technical challenges. The British had already been working on similar concepts and had shared some of their early research with American scientists. Their work had demonstrated the basic principle could work, but had not yet produced a combat-ready device. Tuve established what would be called Section T at the Johns Hopkins Applied Physics Laboratory in Silver Spring, Maryland. The name was deliberately vague for security reasons. Section T's mission was to develop a practical radio proximity fuse for anti-aircraft shells. The team Tuve assembled included physicists, electrical engineers, mechanical engineers, and technicians, eventually growing to over 800 people working on various aspects of the fuse's development. They worked in an atmosphere of urgency that only increased after December 7, 1941, when the United States entered the war. The fundamental concept was straightforward. The fuse would contain a miniature radio transmitter that broadcast a continuous signal. This signal would reflect off any nearby metal object, like an aircraft. A receiver in the fuse would detect the reflected signal. As the shell approached the aircraft, the reflected signal would grow stronger. When the signal reached a predetermined strength, indicating the shell was within lethal range, the fuse would trigger the detonator. Simple in concept, extraordinarily difficult in execution. The technical challenges were immense. First, the vacuum tubes. Every radio transmitter and receiver of that era used vacuum tubes, fragile glass devices containing delicate internal elements. The acceleration forces when a 5-inch shell was fired reached 20,000 Gs, 20,000 times the force of gravity. That meant every component inside the fuse experienced forces equivalent to weighing 20,000 times its normal weight for a fraction of a second. Standard vacuum tubes shattered instantly under such forces. Their internal elements, thin wires and grids suspended in vacuum, simply could not survive. Tuve's team needed to develop entirely new types of vacuum tubes that could withstand forces no vacuum tube had ever been designed to survive. They worked with manufacturers to create tubes with heavier elements, shorter wire lengths, more robust internal supports, and thicker glass envelopes. Engineers tested hundreds of designs, firing them in test fixtures that simulated gun acceleration, examining the failures, and iterating toward tubes that could survive. By early 1942, they had developed tubes designated as VT-158, miniature pentodes specifically designed for proximity fuse applications. These tubes were smaller than standard radio tubes, more rugged and optimized for the specific circuits the fuse required. Second, power supply. The fuse needed electrical power to operate its transmitter and receiver circuits. Batteries of that era were too large, too heavy, or too unreliable. The fuse cavity had almost no spare volume. Every cubic inch was precious. The team developed a special battery design using reserve electrolyte stored in glass ampules. When the shell was fired, the acceleration force broke the ampules, releasing the electrolyte into the battery cells, activating them. This meant the battery had an indefinite shelf life before firing, but would activate automatically during launch. The battery had to provide stable voltage output for the 45 seconds or so that the shell would be in flight, then could be discarded. It was a use once, activation on firing design that solved multiple problems simultaneously. Third, the antenna. The fuse needed to transmit and receive radio signals, which required an antenna. In a conventional radio, antennas are external structures, wires or rods extending from the device. The proximity fuse had no external structures. Everything had to fit inside the fuse cavity or within the shell's body. The team developed an antenna design that used the shell's metal casing as part of the antenna system. The nose of the shell was modified with an insulated section that served as the actual radiating element. This was a clever solution that required careful engineering to ensure the antenna would radiate efficiently at the chosen frequency while still maintaining the shell's structural integrity and aerodynamic properties. Fourth, the radio frequency. The team chose to operate at approximately 200 megahertz in the VHF band. This frequency was high enough that the required antenna could be small and efficient at the shell's dimensions, but low enough that they could build transmitter circuits with available vacuum tube technology. At 200 megahertz, the wavelength was roughly 1.5 meters, which meant a quarter wave antenna would be about 14 inches long, reasonably achievable within the shell's geometry. Fifth, the circuit design. The transmitter had to be simple, reliable, and consume minimal power. The receiver had to be sensitive enough to detect weak reflected signals, but not so sensitive that it would trigger on random noise or interference. The detonation circuit had to be absolutely certain, triggering the explosive only when the signal conditions were correct, never failing to trigger when they were correct. Engineers designed and tested dozens of circuit variations, evaluating performance under varying conditions, measuring reliability across temperature ranges, testing resistance to vibration and shock. By mid-1942, Section T had working prototypes that survived firing and successfully detected targets under laboratory conditions. Now came testing. The fuses were loaded into 5-inch shells and fired at drone aircraft over the Chesapeake Bay. Early tests had mixed results. Some fuses failed to function at all, destroyed by the firing forces despite all the engineering that had gone into making them rugged. Some functioned but failed to detect the target aircraft. Some detected the target but triggered too early or too late. Each failure was analyzed. Each successful test provided data on what worked. The team iterated constantly, improving designs, refining circuits, strengthening components. One persistent problem was premature detonation. Some fuses would trigger immediately after leaving the gun, detonating the shell just a few hundred feet from the ship. This was catastrophically dangerous. Investigation revealed that the fuses were detecting the reflection of their own radio signal bouncing off the ocean surface. When the shell's trajectory brought it close to the water, the reflected signal from the surface was strong enough to trigger detonation. Engineers added a time delay circuit that prevented the fuse from arming until several seconds after firing, ensuring the shell would be well clear of the ship and far from the surface before the detection circuit became active. Another problem was orientation. If the shell was tumbling or spinning in flight, the antenna's radiation pattern would sweep through space irregularly, potentially missing targets or producing inconsistent detection ranges. The shells had to be aerodynamically stable, maintaining predictable flight orientation. This required coordination between the fuse designers and the ammunition manufacturers to ensure the shells would fly correctly with the modified nose sections required for the fuse antennas. By late 1942, reliability had improved dramatically. Fuses were functioning in more than 90% of test firings. Detection ranges were consistent. The detonation logic was working correctly, triggering when shells passed within lethal range of drone aircraft. The team was ready to move toward production. But production presented its own challenges. The Navy wanted these fuses in massive quantities, hundreds of thousands per month eventually. The design had to be manufacturable at scale, with components that could be produced by companies that had never built anything like this before. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The first combat test of the proximity fuse came not in the Pacific but in the Atlantic, and not against aircraft but against a threat even more pressing in early 1943. German U-boats were sinking merchant ships faster than the Allies could replace them. The Battle of the Atlantic was reaching its crisis point. While the proximity fuse had been designed for anti-aircraft use, Navy planners recognized it might have another application against surfaced submarines. In January of 1943, the cruiser USS Helena was equipped with proximity-fused 5-inch ammunition and deployed to the South Pacific with orders to test the new fuses in combat conditions. The orders were explicit and unusual. The fuses were to be used only over water, where if a shell malfunctioned and fell unexploded, it would sink without trace. Under no circumstances were proximity-fused shells to be fired over land where they might be recovered by the enemy. The technology was so secret that risking enemy capture of an intact fuse was considered unacceptable. Ships equipped with these fuses carried instructions to jettison all proximity-fused ammunition if capture appeared imminent. The fuses were marked with special identification codes. Crews were briefed that the ammunition was highly classified and its nature was not to be discussed. On January 5, 1943, Helena was operating near Guadalcanal when Japanese aircraft were detected approaching. The ship's 5-inch guns were loaded with the new ammunition, mixed with conventional time-fused shells, so that gun crews would not know which shells were proximity-fused and which were conventional. This was deliberate operational security. If the new fuses proved dramatically more effective, the crew's combat reports would document that effectiveness without revealing the specific technology. Helena opened fire. Gun crews loaded, aimed, and fired as they had been trained, following standard anti-aircraft procedures. They set time fuses on shells when ordered to do so, not knowing that other shells loaded into their guns had no external time setting because they carried the new proximity fuses. The results were immediately apparent to observers on the ship's bridge and in the fire control stations. Shells were detonating close to target aircraft with remarkable consistency. Aircraft that would normally have flown through barrage fire were being hit by fragments. Some were destroyed outright. Others were damaged and forced to withdraw. Post-action analysis showed that proximity-fused ammunition was achieving hit rates approximately 5 times higher than conventional time-fused ammunition under similar conditions. 5 times. Where it had previously taken thousands of shells to bring down a single aircraft, it now took hundreds. Where anti-aircraft fire had been a matter of creating zones of exploding shells and hoping aircraft flew through them, it was now becoming a direct engagement system where shells reliably exploded near their targets. The implications were staggering. Through early 1943, more ships were equipped with proximity-fused ammunition. Combat reports confirmed the initial results. The fuses were reliable, they were effective, and they were changing the calculus of naval air defense. Japanese pilots began reporting to their commanders that American anti-aircraft fire had suddenly become far more accurate and deadly. They did not know why. American ships seemed to be shooting more precisely, anticipating movements, exploding shells at exactly the right moment. Some Japanese intelligence officers speculated that Americans had developed superior fire control predictors or better training methods. None suspected the truth, that the shells themselves had become intelligent, detecting targets and choosing their own detonation timing. The Battle of the Philippine Sea in June of 1944 demonstrated the proximity fuse's impact at scale. American carriers and their escorts faced massive Japanese air attacks, hundreds of aircraft attempting to overwhelm the fleet's defenses. American fighters shot down many attackers, but many more penetrated to where they faced the fleet's anti-aircraft fire. Ships fired thousands of rounds of proximity-fused ammunition. The result was described by American pilots watching from above as a turkey shoot. Japanese aircraft were being destroyed in unprecedented numbers. The few that survived to press their attacks faced fighters and close-range defensive fire. Very few succeeded in hitting American ships. Post-battle analysis credited the proximity fuse with a significant portion of the defensive success. The Japanese lost approximately 300 aircraft in the battle, many to anti-aircraft fire that would have been far less effective with conventional ammunition. American losses were minimal. The naval balance in the Pacific shifted decisively. Japanese naval aviation never recovered from the losses suffered when their aircraft flew into zones defended by proximity-fused anti-aircraft fire. The weapon that experts had declared impossible was proving to be one of the most effective defensive technologies of the war. By the summer of 1944, American industry was producing proximity fuses at a rate that would have seemed impossible just 2 years earlier. Multiple manufacturers had been brought into the program. Western Electric, a company known for telephone equipment, was producing vacuum tubes specifically designed for the fuses. Eastman Kodak was manufacturing optical components. Dozens of other companies were producing batteries, circuits, mechanical components, and assembled fuses. The production system involved over 200 companies and tens of thousands of workers, most of whom had no idea what they were building. Security around the proximity fuse program was extraordinary. Workers assembled components without knowing their purpose. Manufacturing was compartmentalized so that no single facility produced a complete fuse. Final assembly occurred at secure locations. The fuses were packaged in containers that revealed nothing about their contents. They were shipped with innocuous designations. VT fuse, the official name, stood for variable time, a deliberately misleading term that implied a more sophisticated mechanical time fuse rather than revealing the radio proximity mechanism. Even as proximity fuses were being fired in combat by the thousands, their existence remained secret. Press coverage of naval actions was censored to remove any mention of unusual anti-aircraft effectiveness. Combat reports were classified. Sailors who served on ships using the ammunition were instructed not to discuss it. The few who knew the full technical details of how the fuses worked were under strict orders. Merle Tuve and his team at Section T continued their work under intense security, refining designs, solving production problems, and developing variations for different applications. The technology proved adaptable beyond its original anti-aircraft purpose. Engineers developed proximity fuses for Army anti-aircraft artillery, allowing ground-based guns to achieve the same effectiveness improvements that Navy ships had experienced. By late 1944, these fuses were being used in Europe. When Germany launched its V-1 flying bomb campaign against Britain in June of 1944, British anti-aircraft defenses, equipped with proximity-fused ammunition, achieved kill rates above 50% against the unmanned aircraft. The V-1s flew straight and level at consistent altitude, making them nearly ideal targets for proximity-fused anti-aircraft fire. Within weeks, the British had developed tactics that destroyed most V-1s before they reached their targets. The fuses were also adapted for field artillery. A ground-burst artillery shell needed to detonate on impact. But an air-burst shell exploding 20 or 30 feet above the ground was far more lethal against infantry in the open, because fragments would rain down from above rather than being absorbed by terrain. Conventional airburst fire required time fuses set based on estimated range to target, with all the inaccuracies that implied. Proximity fuses could trigger automatic airbursts at optimal height above ground. In December of 1944, during the Battle of the Bulge, American artillery equipped with proximity-fused shells devastated German infantry formations that had been advancing in relatively open terrain. German soldiers reported that American artillery had suddenly become far more deadly. They were correct. Shells were exploding above them with perfect timing, creating lethal fragment patterns that conventional contact-fused shells could not achieve. By the end of the war, American factories had produced over 22 million proximity fuses. 22 million sophisticated electronic devices, each containing vacuum tubes, batteries, transmitters, receivers, and detonation circuits, all designed to survive being fired from a gun and all manufactured at a cost that made them practical for single-use ammunition. The production achievement was as remarkable as the engineering achievement. Industries that had never built electronics were producing millions of units per month, with reliability exceeding 90%. The manufacturing system developed to produce proximity fuses would influence American electronics manufacturing for decades after the war. The human cost of the proximity fuses development was measured not in lives lost, but in lives saved. Every ship that survived an air attack because proximity-fused ammunition destroyed attacking aircraft represented hundreds of sailors who went home after the war. Every bomber crew that completed their missions because German anti-aircraft fire was less effective represented men who lived. The technology shifted odds in favor of defenders. It made air attack more costly and more dangerous for attackers. It changed tactical calculations across every theater where it was used. But there was another human dimension to the story, one that Merle Tuve and his team understood even as they celebrated their technical success. They had created a weapon, not a defensive technology or a protective measure, but a device specifically designed to destroy aircraft and kill the men inside them. Tuve was a scientist who had spent his career before the war studying the physics of the natural world, measuring the ionosphere, investigating cosmic rays, pursuing knowledge for its own sake. The war had turned him into a weapons designer. His expertise in radio propagation and vacuum tube circuits had been applied to building devices that killed efficiently and reliably. In later years, Tuve rarely spoke publicly about his work on the proximity fuse. When he did, he emphasized the defensive nature of the weapon and the lives it saved on the Allied side. But colleagues remembered that he struggled with the moral dimensions of what he had created. The proximity fuse was clean engineering, elegant in its design and sophisticated in its execution. It was also responsible for the deaths of thousands of men, Japanese pilots over the Pacific, German aircrew over Europe, soldiers on the ground during artillery barrages. The mathematics of its success were the mathematics of lethality. The Japanese never fully understood why American anti-aircraft fire became so effective starting in 1943. Their intelligence services noted the change, but attributed it to improved fire control systems, better training, or superior tactics. They captured some proximity-fused shells that failed to detonate, but the shells fell into water and were too damaged to reveal their secrets even when recovered. A few intact fuses were captured late in the war, but by then the outcome was already decided. Japanese engineers who examined them after the war expressed shock at the sophistication of the design and the fact that such devices had been manufactured in the millions. German intelligence came closer to understanding the truth. They captured proximity-fused artillery shells during the Battle of the Bulge and managed to recover some relatively intact fuses. German engineers reverse-engineered enough of the design to understand the basic principle. Reports were written describing the American radio fuse and its devastating effectiveness. But Germany in late 1944 and early 1945 lacked the industrial capacity, the resources, and the time to develop a comparable weapon. Even if they had understood the full details earlier in the war, Germany's electronics industry was not prepared to manufacture vacuum tubes ruggedized enough to survive gun launch forces, and their battery technology was inferior to what American manufacturers had developed. The proximity fuse was not just a clever design. It was a product of American industrial capacity and manufacturing expertise that Germany could not replicate. The secrecy surrounding the proximity fuse continued even after the war ended. Details of its design and operation remained classified for years. The technology had implications for future weapons development. The same principles could be applied to guided missiles, to air-to-air weapons, to any system that needed to detect and respond to nearby targets. Military planners recognized that radio proximity fusing was a technology that would shape weapons design for decades. The vacuum tubes and circuits of the World War II-era fuse were primitive compared to what would come later, but the fundamental concept remained valid and valuable. Return to that gunner tracking the bomber at 12,000 feet, adjusting his mechanical time fuse, firing, missing. That was warfare, as it had been practiced for decades. Humans with machines trying to hit other humans with other machines, relying on calculation, prediction, and luck. The proximity fuse changed that equation fundamentally. It transferred the final decision, the moment of detonation, from human calculation to automated sensing. The shell became intelligent in a limited but crucial way. It could detect its target and respond faster and more accurately than any human operator. This was not artificial intelligence in the modern sense. The proximity fuse did not learn or adapt. It did not make complex decisions. It performed one task, detecting when it was near a metal object and triggering a detonator. But within that limited scope, it performed that task with superhuman reliability and speed. It represented a shift in the relationship between humans and weapons, a shift toward automation, toward machines making tactical decisions in milliseconds that humans could not match. The broader significance of the proximity fuse extends beyond its immediate military impact. It demonstrated that focused scientific research, given adequate resources and motivated by urgent necessity, could solve problems previously considered impossible. It showed that American industrial capacity could manufacture sophisticated electronics at scales that seemed absurd before the war. It proved that military effectiveness could be dramatically improved through technological innovation, rather than simply increasing the quantity of conventional weapons. These lessons would shape military research and development for the remainder of the 20th century. The men who developed the proximity fuse were not soldiers. They were physicists, engineers, and technicians who had been teaching at universities or working in corporate laboratories before the war. They were mobilized not to fight, but to think, to solve problems, to create new technologies. Vannevar Bush's vision of organizing civilian scientific talent for military purposes, embodied in the National Defense Research Committee, proved extraordinarily effective. The proximity fuse was perhaps the clearest example of that success. A weapon designed entirely by civilians and transferred to the military as a finished product ready for combat use. Merle Tuve returned to civilian research after the war. He became director of the Carnegie Institution's Department of Terrestrial Magnetism, returning to the pure physics research he had pursued before 1940. But the war had changed him and had changed the relationship between science and military power. The proximity fuse, along with radar, the atomic bomb, and other wartime developments, demonstrated that future wars would be won as much by scientists and engineers as by soldiers and sailors. The nations with superior technology, superior manufacturing, and superior ability to apply scientific knowledge to military problems would have decisive advantages. For the sailors manning anti-aircraft guns aboard ships in the Pacific, for the soldiers operating artillery in Europe, the proximity fuse meant they had a weapon that worked, that gave them a genuine chance against attacking aircraft or enemy infantry. They did not need to understand the physics or the engineering. They simply needed to load the shells and fire. The shells would do the rest. That was the promise of technological warfare, that complexity could be hidden inside systems that were simple to operate, that sophistication could be delivered through familiar interfaces. The gunner tracking the bomber at altitude, calculating lead time, setting his mechanical fuse, that gunner was practicing warfare as it had been known. The gunner loading a proximity-fused shell, simply aiming and firing, trusting the shell to detect its target and detonate at the optimal moment. That gunner was practicing warfare as it would become. One required skill and judgment and constant mental calculation. The other required trust in technology, in devices built by people he would never meet, designed according to principles he might not understand. Both were warfare, but only one was the future. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.